So we're gonna get started with the last talk of Anders Hansen. So.
All right. Does the microphone work now? Very good. All right. So my plan now is that I'm just going to do a little bit of a recap what we did before lunch, because I want that to be fresh in your memory before we get into the new developments. So let me just say a little bit about what we did before. We went through these problems here, and we wanted to ask if we can actually compute solutions to them and know that we're getting a bound on the error. And I have advocated this here quite a lot yesterday, but I also mentioned that these constrained and unconstrained lasso problems are also very popular in the literature. I mentioned that foundations of computational mathematics is certainly not a new thing. It exists a lot in the history of mathematics. And we wanted to essentially ask the question, can we find algorithms that can solve our problem? But I pointed out that this really here is a toy problem, that the true life issues are much more demanding. Namely that in real life, I really have to ask if I can compute even if I have some inaccuracies in my input. So the key question number 2 is that I have any of these problems, and I may have input that comes with some inaccuracy controlled by epsilon hat. And the key question is, can I actually find an algorithm that computes a solution to my problem with some epsilon here? So in other words, I ask for 4 digits. If you need that to be 14 digits or 50 digits, I don't care, as long as you can find a relationship between them and I can halt and I know what I'm doing. Okay. And then we sort of went down the philosophical route and asked what would actually happen if the answer to the question was no. And essentially argued that what could happen is that you can end up spending a long time and not get an accurate answer. And you wouldn't also be able to halt and know when you have the correct answer. But I also did point out that such a failure of the algorithm would only happen for sufficiently small epsilons. And since we're doing scientific computing, we're actually interested in getting something which is reasonable for the application. In other words, could there be an epsilon which may not be arbitrarily small, but still good enough for my application so that it's going to work? And that's why I mentioned this idea of the breakdown-epsilon, which will be the largest epsilon for which any algorithm is going to break down. But if that is reasonably small, maybe we can still work with it. I also mentioned that essentially, if you have a negative answer to question 2, it doesn't mean that you may not be able to compute. What it really says is that you may have to have extra conditions on it. But the algorithm will need to have that as knowledge of the input. And an important part is obviously condition, which it always is in numerical analysis. So I mentioned these well-known concepts of condition. The classical one, the condition of a matrix, a condition of a nonlinear mapping, and also the condition, the feasibility primal, which says something about if I perturb my problem, is it still going to be feasible? All right. And then the theorem, which might be a little surprising, says that actually, even if you have very nice and well-conditioned problems, the answer to question 2 is no. And more dramatically, it says that the breakdown epsilon for these problems is greater than 1/3. And that means that if you want to solve these problems accurately, there are inputs which will make your algorithm actually work for, say, 50 billion years, and you still won't have reached 1 digit. And that may not sound very good, and it might sound a little contradictory compared to all the examples that I showed yesterday, where things actually work very nicely. I also pointed out that if you look at this from a logic point of view, if you actually had a positive answer to this question 2, it does imply the solvability or the decidability of the halting problem, for which, of course, you cannot decide. And it's the same issue also with linear programming. So what we actually have is that we have problems that are logically, formally non-computable, but we do compute with them on a daily basis. And we need to figure out what are we actually doing and why does it work. So we wanted to ask, can we trust our algorithm? And we wanted to ask also, why do algorithms work so well? And do you actually need to worry if you're a practitioner? Should you care? And we did some MATLAB tests where we showed actually there is an issue. It is not very hard to make any modern software fail. And it's not because the people who have designed the software didn't do their job. It is a fundamental barrier. So regardless of how good you are, there will be an input. So if you create an algorithm, there will be an input that is going to make that algorithm break. And what we're going to try to figure out is, well, I would like to find inputs that won't make the algorithm break. And I pointed out that if you try to be nasty to MATLAB's / command, which computes a solution to a linear system, there is a built-in warning, which is very nice, because it tells me that, OK, in this case here, I have been bad, and I've given it a bad problem. The question would be, why don't I have a warning like this for, say, linprog that solves linear programming? And I argue that the reason why that's the case is that there isn't a way of doing this. So what I'm going to try now and spend the next hour and a half is to figure out what are the good problems and what are the bad problems. So I mentioned this plot here, which I showed you yesterday. And I asked you if I really gave you a good justification for essentially arguing that it was this method here that is better than the other one, because I actually don't have an oracle that gives me the solution to the problem. I have to use an algorithm to produce these images. And if I cannot guarantee that the output of my algorithm is done with a certain accuracy, how can I actually safely say that this method here is better than the other one? And I pointed out that this is happening on a, well, maybe a daily basis is an exaggeration, but on standard imaging conferences, we do show images and conclude that what we have done is better than the competitor based on plugging something into the algorithm. The question is, how do I actually know that this was really a methodological difference and not just me being a pinhead when I plug this into my algorithm? So I also asked, how do you set the halting parameters in your code when you produce images? And, well, it's not completely unheard of that we just simply try it. Well, it looks pretty, nah, it doesn't look so good. Let me try it a little again. Maybe tweak a little bit with some parameters, and now it looks good. So that's the one that goes into the paper. But we don't write that, do we? OK. So now we're going to try to figure out what is really going on and when can I actually rely on my computation. And what I'm going to try to get through here is that sparsity is a key component. And also the concept of this breakdown-epsilon. And I'm also going to discuss this a little further on, namely, do practitioners have to change their approach? Well, actually, if you're going to claim, or if I'm going to claim, that my method is better than my competitor's method, I better be pretty sure that I actually can guarantee that what I've done with the algorithm is perfectly sound. Because otherwise, I'm just coding something up and hitting return. So just before the break, we talked a little bit about the issue of having several minimizers. And I introduced this condition number here, which is the condition number which is related to the problem of having several minimizers. So if I have a unique minimizer, and I perturb my problem, and I still have a unique minimizer, that might be something which is advantage. In fact, some people in optimization consider problems for which you have several minimizers ill-posed. I'm not suggesting that it is ill-posed, but this you will find in the literature. So this is the RCC condition number, which is well known and pretty well understood. And this gives us now the 4 different types of conditions that I can talk about when I'm interested in actually solving my optimization problems. OK, so I mentioned that this book here contains a lot of these things. It's a very nice book. And this is where we ended. where we said, if we're going to do compressed sensing, which we spent the whole yesterday doing, maybe it would be of interest to figure out if we have the conditions that you have in compressed sensing, would that allow us to actually have some positive results? Could I then actually make sure that I code things up, I have a halting criterion, and I guarantee you that things are accurate? Seems like a reasonable place to start, right? So I mentioned that the robust null space property is a property which is a core part of compressed sensing. I didn't mention it yesterday. I mentioned the RIP. The RIP is slightly stronger. But if you actually look at the standard compressed sensing theory, it is the null space property that is used to prove all the theorems. So RIP implies the null space property, and then you say, oh, if I have the RIP, then I have the null space property, and here are the proofs. And you're getting exactly the same kind of estimates, namely these things here. You have some constant that depend on the rho here, and then you have the S-term approximation, and then here is the noise term. But this is only for recovery. It assumes that I have an oracle that can give me a minimizer. And now we're going to try to figure out, can I actually cook up an algorithm that's going to give me that minimizer, or an approximation where I know something about the error? So what I'm going to do now is that instead of listing a whole bunch of theorems, I'm going to show you these results in a table, and I'm going to try to discuss them with you. And I encourage you, if there are questions now, please interrupt me so I can address them. So the first line here says that if the condition number, the standard of AA star is bounded, if this feasible primal condition number is bounded, the condition number of the mapping itself, and everything here is bounded, I'm still not secure. This was the first theorem that I showed you. And what it tells you is that regardless of how good you are at coding, you won't be able to break this breakdown-epsilon, and it will be greater than 1/3. So there will be an input for which your algorithm will never be able to give you better results than 1/3. But now I want to show you a positive result. So check this out. Now, if I have, my input now is y, which comes from a sparse vector x, and my A here is either a Bernoulli matrix, so that means that it has -1s and 1s, or a Hadamard. So this here is a random guy, this here may not be a random guy, but it doesn't matter for the purpose of computability. If I have these conditions here, actually the RCC condition number is infinite. I am arbitrarily close to having several minimizers. Yet the answer to question 2 is yes. I can perfectly fine compute problems that are of this form here, but that condition number is infinite. And what that tells me is that even if I had an oracle that could check my input and say, is this well conditioned? I could have that these things are all nice, and I won't be able to do it. This could be infinite, and I'm still perfectly fine. Please.
And the question, like the rho function in your RCC, isn't that the cardinality of the set of minimizers?
Oh, no, it's the distance.
Okay, sorry. Okay, so
it's a good point. So here's the key thing here is that if you have a unique minimizer, so in a lot of the literature in optimization, it will say it is good to have a unique minimizer. And you would actually also have to have robustness, meaning that if you perturb your problem a little bit, you should also make sure that you only have a unique minimizer. So you're not ending up with suddenly having several minimizers. So you're dividing by the distance here.
Okay, that makes sense.
Yeah, and what I'm saying is that I can very simply have problems of this form here, where that condition number is infinite. And you would think that if that condition number is infinite, then the question should be no, right? And then I say, no, actually, it's perfectly fine. And what that means is that I can't really say that by knowing these condition numbers of my problem, I know if it's a good or a bad problem. And now you could have said, well, are these problems here in some sense contrived? I mean, Bernoulli and Hadamard matrices. These are not contrived examples. This is the core part of compressive imaging if I have binary measurements. This is what we use. So, in fact, if I want to compute with these guys, it's perfectly fine, and I get a positive answer to the question, yet the condition number is infinite. Now, if I have that the condition number, the RCC condition number, this one here, is bounded, and everything else is bounded, but I'm not considering the other condition numbers. If I work with basis pursuit, then the breakdown-epsilon is still 1 over 3. So I can't single out and say, well, if I have that is good, then things are going to be fine. So what it teaches us is that if we're going to find a way of determining which problems are good and which problems are bad, we have to look for different properties. And that's a little delicate. Now, here's another positive result. If y is equal to a of x, and x is S sparse, and A has the robust null space property of order S, actually the answer to question 2 is yes. I can do it. Great. And you, in some sense, expected that, right? It should work. I mean, the matrices that we've been working with in compressed sensing, we have the case that these are actually going to give us nice problems. So, indeed, they do. But is it clear that if you now change that delta, and that the delta is non-zero anymore, will that change the answer to the question? And it does, and that was quite a bit of a surprise for us. So this here is the previous one where delta is equal to 0. So in this case here, actually, it is yes. But if I change the noise parameter just a little bit, then suddenly the answer to the question is no. That is a little strange. But there is a remedy here. And the remedy is as follows. This breakdown-epsilon now is controlled by a constant times that epsilon. Sorry, that delta. This constant here depends on the rho and the tau in that robust null space property. And typically for reasonable choices of that, that's of order 10. So that means that if, say, this is 10 to the minus 5, that breakdown epsilon is no worse than, say, 10 to the minus 4. So that might actually work very well in applications. And that's why I have this asterisk on the no. This is not really a negative result. It's a negative result with an asterisk. It says that I can't get arbitrary accuracy, but it is controlled by this delta. So I can actually get good accuracy if I set that parameter reasonably small. And that's what we do. So I'm not saying that you can't use basis pursuit with noise and compressed sensing matrices. You should do it. And it works great. But you cannot get arbitrary accuracy with it. But I'm not interested in having, say, 16 digits. I might be very happy with, say, 4 or 5 digits. And in that case, I'm good. And that's why it actually works. So if you code this up, and you try your compressed sensing problem, and you hit return, and you're solving this with one of these matrices, you won't be able to get more than, say, 4 or 5 digits. But so what? That might be very well suited for your imaging problems. And I'm going to discuss that in a second, why that is sufficient. So now you can ask, what if you change the conditions a little bit? What is going to happen? Right. If I change my conditions here, suppose now that I don't have the robust null space property with rho strictly less than 1, but it's actually bigger than 1. What happens then? Well, in that case, the answer is no. And when I've shown here the breakdown-epsilon greater than 1, that means that it is greater than 1, but we don't have exactly the bounds on it, working on it. It's a tough problem. In general, you'll have this phenomenon here, and this is important to get through. And that is that if your input has the following properties, there exists an input so that you have more than one minimizer, and then for some epsilon greater than 0, if you can perturb your problems in the following way, with a semi-definite diagonal matrix D here, and so that you're still in the input, this gives you automatically a negative result and a negative answer to question 2. So this shows you the delicate issues with having several minimizers. But that doesn't mean that you may never be able to work with it, because in this case here, the breakdown epsilon will always be greater than 0, but it can certainly change depending on your class. But the fascinating thing, and this happens for both basis pursuit and unconstrained lasso. For constrained lasso, you can have input conditions that do satisfy this, yet the answer to the question is yes. So suddenly I have a slightly different problem, but with the same conditions, and then the answer to the question is yes. Okay. Just kidding. Now, you can ask also, what happens if I don't have a perfectly sparse vector? Because I argued yesterday that in a lot of cases, you will not have a perfectly sparse vector. You have sparse plus something, right? So what is happening in that case? My input now is an x1 plus x2. And this is my input. A now has the robust null space property. But I have a norm. I have a bound on this x2 part. The answer to question 2 is still no. But again, it's controlled. And of course, I can also combine these things together. So if I have both noise and a program here, I can collapse these guys together. And what that says is that essentially, in the cases where you have compressed sensing matrices, you may not be able to get arbitrary accuracy, but you're going to get reasonable accuracy. Essentially on the order of the same error that you get in the recovery. Both in this part here and due to this part here. And that is essentially why things work. So when we're in the good areas where we can recover, you can also find algorithms that is going to compute it. The question is how, which I'm going to get to in a second. So for linear systems, I mentioned before, then the answer to question 2 is always yes. And for linear programming, it is no in general, even if you have things that are well conditioned. OK. So why do many algorithms work? So I've argued that sparsity is a key component, which is great because sparsity is a key component in compressed sensing. So indeed, if I have a robust null space property and I'm solving basis pursuit without noise, I'm all good. I could have a noise parameter, then the breakdown epsilon is still going to be controlled, meaning that you may very well be able to do computations. So you're on the safe side. But what I haven't addressed here is, are there other issues than sparsity? You have an optimization problem, and I'm saying that for certain conditions where you have sparsity, it will be good. But I haven't said anything about other conditions, and that is completely open. OK, I'm going to show you some images later on. So now, if you were in signal processing, you may not care so much about how did I actually get the lower bounds, but you might be interested in how did I get the upper bounds. In other words, how could one argue that my algorithm is going to halt, and you argue that this is the accuracy that you're getting? How is that possible? So what we did was to do the following, to assume essentially the weakest possible conditions on an algorithm to see if we can get upper bounds. So the only thing that we require from the algorithm is that it can solve a basis pursuit problem with some noise parameter epsilon in the following way, that it spits out some xn that doesn't have to be feasible. It has to be asymptotically feasible. And then that the objective function converges as n tends to infinity. But of course, with no rates. I don't assume anything. So even with that weak conditions, it is possible to use the knowledge that you have, that your matrix has the robust null space property, and say, here is the halting criterion, and here is the accuracy that you need under input, and it will guarantee this is actually accurate. And what that suggests is that the upper bounds that we have on this breakdown epsilon cannot be sharp, because we used some very, very general things. And I will challenge people who are interested in optimization, can you beat us? I think that there's a lot of way smarter people here than us, and it's very likely that you can actually get a better bound than that. And you can turn that question around and say, well, if you do have an algorithm, does it actually touch the boundaries of what you can do with a computer? Do you actually get that breakdown epsilon with your algorithm? OK, so now we're going to go back to a little bit of practical issues. So I mentioned before lunch regarding the question about how do you halt? And I told you that the way we halted when we did this experiment was simply that we hacked the code, and we had a little sneak peek. Right? So every 50 iterations, we will look at it and say, well, no, it doesn't look so good. Let's run it a little longer. Right? But now we actually know that we can halt, and we can make sure that what we're doing is sound. The matrix used here does not satisfy this robust null space property per se. It satisfies a robust null space property in levels, which is a little bit what I discussed yesterday. And with that, we can actually compute. So this problem here actually has the breakdown epsilon is less than 10 to the minus 4. So it is possible to say this here is actually computed with an error which is no worse than 10 to the minus 4. And I can do the same thing with this. This is just a linear system. And that means that if I'm now going to say that this method here is better than that method, I can actually do that. Because I know that whatever is spitting out here is actually to that accuracy. But now you may ask, why is 10 to the minus 4 sufficient? I mean, maybe I should have 10 to the minus 8. So why can I work with 10 to the minus 4? Now, if you do the following experiment, take this image, or your favorite image. Zoom in to a pixel level. So that is a grayscale, which represents a number between 0 and 1. Now take that number and perturb it in the 4th digit. See if your eye can actually spot any difference. And you won't be able to see any difference. So of course, if you zoom out of that image, there's no way that you can see any difference. So if this here is an image that's supposed to be used by a radiologist who has a human eye, and if that human eye cannot distinguish between something which is computed with 10 to the minus 4 error, well, I can't do better. So if I'm doing an image, and I can say that I am 100% certain that the computation is done to 4 digits, fine. Then I'm done. And in that way, I can actually say that, yes, the method used for this here is giving me the difference. It is not that I coded this up and I did a very poor job. Did that make sense? So I mentioned this image here yesterday. I don't know if you remember, because I wanted you to keep this in the back of your head, right? And the question here is, so I run, or we run, the team run, a lot of different simulations here. And suppose that I was going to make the argument that one is better than the other one. How can I make that argument? I have just run these codes. I have no idea that I've actually computed what I have here to any precision. In fact, I downloaded all these. I haven't coded this up. I just downloaded them, and I set some parameters and hit return. I suppose that we went to an imaging conference, and you would have these different teams talking about their methods. Could it be that you saw different outcomes? Because, well, you might have set your code slightly differently. So what would be reasonable is that if I'm going to make a claim that my method is better than the competitor method, or the competitor says that their method is better than my method, it might make sense to say, well, I can make that claim if I can guarantee that I've actually done the numerics correctly. And if I haven't, then I should at least reveal that and say, actually, I have done these simulations, but I cannot really deduce more than, well, I've simply coded this up and set some parameters. So this is the part where I do suggest that, yes, if we're going to make predictions, either about my method or somebody else's method, it is a crucial part that we actually know how to set the halting criteria and that you do get an accurate computation. OK, so I'm just going to show in one other case. Let me just see how I'm doing now with time. Oh, yeah. OK, good. I haven't talked about, let me just go back very quickly. I haven't talked about lasso that much. I have mostly talked about basis pursuit in connection with compressed sensing. And I haven't talked about this part here. Now, lasso you will find a lot in statistical estimation. And I haven't given you any sufficient condition for this to work. And the important part is that you need to have single out the sufficient conditions that people in the field are actually interested in. So in compressed sensing, well, we have the robust null space property and stuff like that. In statistical estimation, the typical conditions that you have on your input is called a dual certificate. If you remember the previous talk, there was mentioning of the dual certificate for recovery problems there. And it's a similar thing with lasso. So a very standard condition is what's called a dual certificate. So I have now an input matrix A, and I have some psi here that I would like to estimate. And what I'm requiring here is that I have this thing here bounded away from 1 with some parameter alpha. So I have some vector which is supported on some set, and then I have to have this condition here. So this is invertible, and this guy here is bounded away from 1. And also that the smallest singular value that I have here is also bounded away from 0. So I know this guy here. And with that kind of conditions, you can also solve the unconstrained lasso problem perfectly fine. So these are sufficient conditions that you typically find in the literature in lasso. And it also says, in that case, you're safe. So I just want to sum up essentially with all these different kinds of paradoxes, that for basis pursuit, you are essentially in good shape all the time when you're working with sparse problems. But it's not completely clear how you do set this in your code. And we haven't specified this here. It's a little technical, but it can certainly be done. And well, we will publish a paper on this from a sort of applied point of view, which shows exactly how this is going to be done. So I'm going to just wrap up this part here, because now I'm going to talk about a slightly different problem, which I hope that you will find interesting. I just want to essentially mention the consequences here. So essentially what is going on is that there is a very rich classification theory for describing the boundaries of what computers can achieve. So the foundations of computational mathematics is a crucial part of understanding what you're doing in modern optimization. And the key issue is that you will want to figure out for which problems you can actually do things where you have a positive results. And if you do have a negative result, the question is, what is the breakdown-epsilon? And these things are essentially key issues for practitioners if you can actually know what you're doing with your code. I just want to mention that these issues here are not specific issues. You will see this in linear programming, semi-definite programming, everywhere. Essentially anything that is based on atomic norms, so you'll see this when you have a nuclear norm, for example, you'll have all these kinds of phenomena that you will have a general negative answer to question 2, but then when you put conditions on, you can be good. And the same issue here is that how do you find the breakdown epsilons for all these kinds of problems? And sparsity is not only an important issue for signal processing in general, it is also a key part to understand what you can do in modern optimization. But I should also say that there might be other conditions. So what we're doing is that we're computing things that are on some bizarre manifolds that we really don't really know how to describe, but sparsity gives us some kind of conditions. All right, okay, so now I'm going to change gear a little bit. And you may think that I've gone completely nuts now because I'm going to talk about computer-assisted proofs. And how on earth can that be of interest to anybody here? Right. Well, it intrigued me, so this is a little bit of general history of mathematics, but it does have an interest, I think, to people who are interested in optimization and certainly linear programming. So, have you ever heard about Kepler's conjecture? Totally fine if you haven't. I had no idea. Kepler's conjecture is a big deal. It dates back to the 17th century, and it's a packing problem. It's a packing problem. It simply asks, how can I store snowballs or oranges or cannonballs in the most efficient way? And most efficient means that the waste space that you're ending up when you're stacking should be as small as possible. So you're essentially stacking them up, and you will like it to fill the space as much as possible. So you're talking about the filling ratio or the filling percentage. So if that's 100%, you're filled up the space completely. Great. Of course, that's not possible with spheres. And the question is, what is the best packing you can ever get? And the conjecture is that this is, so it's not unique. There's at least 2, could be more. But this here essentially are the optimal ones. And that gives you a packing percentage of 75%. So why is this of interest? Well, it is of interest if you would like to get a Fields Medal, for example. So by default, that makes it interesting. And why on earth do I care? And why do I present this here in a workshop where we're interested in modern mathematics of information, right? OK, so here's a little bit of history. I didn't know this until recently, by the way. So if you've never heard about this, it's totally fine. And it will be totally natural, indeed. So the reason why Kepler's conjecture is of interest is that it can be verified by computing finitely many linear programs. So now you see there's a link. So what you can show, well, what actually Thomas Hales showed, building on previous work, was that you can verify Kepler's conjecture by solving a finite set of linear programs. And finite meaning in the orders of, I think, hundreds of thousands, so it's substantial, but something that you can do in finite time. Well, hopefully even before you're 40, so you can go and collect your medal. And the interesting part here was that, so he submitted a paper called A Proof of the Kepler Conjecture, and he submitted it to Annals of Mathematics in 1998. And what happened was that after 5 years of refereeing, there was a committee of 12 people. And after 5 years of wading through 120 pages, they concluded that they were 99% sure that the proof was correct. Yet, even with that uncertainty, the paper was published in Annals. And here's the interesting thing. If you look at the Annals paper, it doesn't come with an asterisk saying, hey, we were just 99% sure. It is called On the Proof, or A Proof of Kepler's Conjecture. So why am I interested in this case here now? Well, I'm interested in, first of all, why were they only 99% sure? You might be interested as well, right? So why were they only 99% sure? Because, oops, And here is the paper. Ah, darn. Okay, you can. Here's the paper. It is 120 pages long. So what I'm going to do for the next hour is that I'm going to read it out loud. And you will all fall asleep. Okay. So I think this in the paper is pretty much page 80 something. So you have to read quite a lot to get here. And I have to admit, I didn't do that. But I was very interested in how he did the numerics. So may you. We're all interested in linear programs, aren't we? Okay, so here's the error analysis. So first of all, he says that the variables, the input in your linear programs here, are going to be the dihedral angles. Okay, that is going to be what I have in my A and B and C. That's the input in my, actually not the C, just A and B. And then it says here, check this out. First of all, the dihedral angles around each vertex sums to 2 pi. That's not a big surprise, right? Because I'm working with spheres, so that you have pi in there shouldn't be a great surprise. But what that tells me is that if I'm going to have finitely many of these input and they're going to sum up to 2 pi, I have input, which is not a rational number, right? I have input which is not exact. You see where I'm heading, right? Now we're going to go further on, and we're going to look at how does he solve it. And he says floating point arithmetic was used freely in obtaining these bounds. The linear programming package Cplex was used. Now if you actually look at this here, this is it's a commercial software. It's great. And that's what he used. And then here, I'm going to show you. However, when the results obtained could be checked rigorously as follows. There's a footnote. The output from each linear program that has no exceptional regions, I don't know exactly what that means, has been doubly checked with interval arithmetic. Okay, that's good. But if I don't know the accuracy of the input, that doesn't give me very much. So I'm essentially asking now, can you guarantee, because this is not a code that somebody's running for an imaging conference. This is the proof, right? So you need to check. I'm not suggesting that they couldn't check it, but you need to check. You need to know. So he says, and here's the interesting part. If epsilon is 10 to the minus 8, he's happy. So the accuracy parameter that he's running in the code is 10 to the minus 8. Not 10 to the minus 4, but it's 10 to the minus 8. And the question is, can we believe the proof? And the committee said that they were 99% sure, but not completely. And this is the issue. So, given the lower bounds that I just talked to you about, does that have an impact on the result of checking the Kepler's conjecture? So, actually, if you read carefully what he does in the paper, he does not need the minimizers. He can simply solve the objective function. The lower bounds that I've shown you today are all about getting the minimizers. So he's good. It's fine. There is a missing part, though, because this summing up to 2 pi means that even if you compute your minimizers, the objective function, you need to know that the tiny little perturbation that you have in your input is not going to change your objective function too much. But you're asking for 10 to the minus 8. And that means that you need to say, well, then I need some accuracy on my input. So these bounds does not violate what is done in this paper. But it's of interest that it took them 10 years to complete the paper. So in 2015, on the archive, there appeared a new paper, which is called On the Formal Proof of Kepler's Conjecture. That has now been published as of May 29th in Forum of Mathematics Pi, which is another top-level journal on the level of annals or JAMS. So now it has actually been solved. I haven't read the whole paper, but now they've taken care of the numerics. It did take them 10 years. But it's still a computer-assisted proof. And it says, here is your 10 to the minus 8. And I assume that they have now covered all errors and say, you can test this, you can run this, and here is the proof of Kepler's conjecture, and it is true. Now there's two interesting things here. One is that it's hard to get a Fields Medal because they've spent so long time on that, and he is now older than 40 years. The other interesting thing is that they only asked for 8 digits. And that is important because even in the case, let's suppose now that he needed the minimizers. I said that he's fine because he actually needed the objective function, okay? But suppose he needed the minimizers. Suppose somebody else needed to compute minimizers of linear programs to prove their conjecture. Could they do it? And the thing is that, yes, they could. If you required something like that, and your breakdown-epsilon was smaller. So the point here is that, yes, we have optimization problems that are difficult. They're even formally non-computable. If you let an army of logicians loose on this, they will say it's non-computable. But that doesn't mean that you can't use it, nor that you could actually use this in a computer-assisted proof. If you can say, here is the accuracy I need on my input, and here is how I halt my algorithm, and if I need 10 to the minus 8, and if the breakdown epsilon is smaller than that, you can actually do it. So I thought that was a little cute little thing that I wanted to point out. And now I'm going to get into some of the questions that were asked before lunch, namely complexity theory. So I could essentially split up this question 2 into 2 other questions. I could first ask, this is the question that I actually asked, if I have some input error, can I still have an algorithm that can compute an approximate solution such that for an arbitrary epsilon, the output will be no further away than epsilon from a true solution? That was the question I asked. Suppose that the answer to that question is yes. I've been talking about that the answer to that question could be no, but suppose that yes. Now I'm interested in having an algorithm that is optimal. I would like to have some complexity theory for it. But just because the answer to the question is yes, that doesn't mean that I have a uniform bound on the runtime. So now what I want to ask is an even more difficult question. Does there exist an algorithm that has a uniform runtime? It obviously depends on the input, epsilon, that I'm saying. I want 4 digits, and I'm asking, can you make sure that you have a uniform runtime? So if I give you a problem in, and I'm asking for 4 digits, it's not going to spend more than a week or 2 minutes, right? So this here is obviously a stronger thing to ask. Does that make sense? Because I want my code to halt in finite time. So that means that I can essentially split these breakdowns into 2 different phenomena. If essentially both 1 and 2 break down, well, that means that it is impossible to determine when the algorithm should halt to achieve an epsilon. And hence, you have no idea what you're actually getting out. But the other one, if the second one breaks down, that means that you can have arbitrarily long time to solve it, even if you eventually could halt and say, well, I can get the epsilon accuracy if forced, but it could take me 50 billion years. So what I want, obviously, is a positive answer to this question. And only when I have that, I can actually start talking about a complexity theory. So you can split up these ideas about these breakdowns to be the strong breakdown epsilon. This is when you actually cannot halt. You have no idea what you're getting. And then there's the weak breakdown epsilon, which says that's the failure of the second condition, that you don't have uniform runtime on your algorithm. And then the question is, I would like to have bounds on this. Right. So obviously, if your strong breakdown epsilon is greater than delta, then of course the weak breakdown epsilon is going to be greater than delta. And likewise, if your weak breakdown epsilon is less than or equal to rho, then of course the strong breakdown epsilon is going to be less than or equal to rho. And now I can ask the question, if I have an epsilon here, which is greater than the strong, it should be the weak, not the strong. That's a misprint. How fast can you get to that epsilon accuracy? So in other words, I'm going to run my code to solve my compressed sensing problem, and I want to have 4 digits. What's the fastest you can get? So now we can essentially start talking about a complexity theory for optimization problems for which you actually may not be able to solve completely accurately. Did that make sense? So if I'm just running my standard code, I want to make sure that I can do this fast, and the question is, what's the fastest you can do? Okay, so I have 40 more minutes. I probably won't be able to cover everything, but what I want to do now is to give you a little bit of a feel of how you talk about these lower bounds. Are there any questions now before I start on that, because that would be sort of a natural wrap-up? Okay, so let me continue. So what I've been talking about so far are upper bounds on essentially how we can make sure that the algorithms work. And you may be curious, how do you actually show that things break down? This is not a part of signal processing at all. This is a part of a greater program, which essentially stems from Steve Smale's program on finding the foundations of scientific computing. But it does start with Hilbert. So what I'm going to do now is I'm going to give you a little bit of a historical background, and I'm going to give you a little bit of a theoretical issue to understand how these lower bounds actually work. So Hilbert, as I mentioned previously in the talk, Hilbert started by asking, can a computer decide things? For example, if you have an finite input, can you always find a computer or a program that determines if the statement is true or not? And this is what starts the whole field about decidability and computability. And if you look at the history of mathematics, for example, the question about the Diophantine equations, which I think was Hilbert's 10th problem, I might be wrong with the numbers there, that is a decidability problem. It was solved in the 70s, a very big result. And there's essentially tons of problems like that regarding decidability. Does there exist an algorithm or not? So when Hilbert asked these questions, this was when essentially Turing made his greatest contributions. And the first one is that actually to make Hilbert's question exact, you have to define what is an algorithm. Because it can be many different things. And then what Turing did was that first by defining what he meant by an algorithm, which is what we now know as a Turing machine, he showed that, well, you cannot use a Turing machine to essentially find a debugger to figure out if a computer program is going to halt or not on its input. So this was the halting problem. Now, I should mention that at the time, Turing was not the only person. There was tons of different people who worked on this. You may have heard about the Church-Turing thesis, which I'm going to address in a second. But there were a lot of different people who worked on the concept of computability or decidability. And it wasn't like you had a lot of different competing theories, and essentially Turing just won because he had the nicest theory. They turned out that they were all equivalent. It is just that Turing's theory was so intuitive, and it even came with a physical machine. And if you never heard about a Turing machine, That's totally fine. I had no idea about the Turing machine when I was in grad school or even in postdoc at all. This is actually a Turing machine, and this is the foundations of what we call an algorithm. You can actually look at this as a physical device. And that's why, essentially, Turing, I wouldn't say won the race, but why this is now the consensus of what we call a recursive function. A recursive function is a function that can be computed with a Turing machine. Just out of curiosity, how many have heard of a Turing machine before? So there's quite a lot. Very good. Excellent. Good. Now, so do you guys know how a Turing machine works? Because I had no idea. So this is a Turing machine. And what you have here is the input tape. The only non-physical part with the Turing machine is that this input tape can be infinite. That's the only non-physical part. On the input tape, you can have only ones and zeros. And here is the sort of the scanning head. The head can read the 0 or a 1. And then there's sort of a brain here. And that brain is containing several stages. And it contains a finite set of instructions that is of the form read, or write, or erase, move to the left, move to the right, or stay in the stage you are, or go to another stage. And with those instructions, you can write any for loop, any while loop, any arithmetic operations, and essentially what you do on a computer is what you can express with a Turing machine. So this is the definition of an algorithm. And it's important to have that in our back of our heads when we talk about the existence of algorithms. Right. Okay. So this is the physical Turing machine. And here is what you will typically see in a textbook. Here is the input tape. Here is the scanning head. And here would be sort of the brain machine with finite number of states. And you have to have at least two states, but 2 states is equivalent to k states, at least as long as k is greater than or equal to 2. So this is the concept of the foundations. And I just want to mention the halting problem again. The halting problem is the problem determining from description of an arbitrary computer program and an input whether the program will finish running or continue to run forever. And Turing showed that, well, you can't do that with a Turing machine. OK. So is there more to these foundations than just a Turing machine? Right. So in the 80s, some people pointed out the following, that if you take a numerical analysis class and say you would like to analyze Newton's method, have you ever done that? You've probably done that in some calculus class, right? We've all done that, right? Even you draw even some lines and see, OK, this is going to converge. And the point that was made was that, do you actually work with a Turing machine when you're going to do that? If you've taken a class on numerical PDEs, or even a class on optimization problems, do you actually work with a Turing machine? So as I mentioned, when I was a grad student, I took a lot of different classes in applied math and numerics, and I never heard about a Turing machine. So what you actually do in real life, when you analyze problems in numerics, is that you assume that you work with real numbers. And in fact, if I plug things in on my computer, I'm actually not working with a Turing machine because I'm not working with exact things. I'm working with floating point all the time. I am pretending that I work with real numbers, but I don't do that. I have floating point representations of them, but it's not an integer representation. So what happened was that in the 1980s, Steve Smale started asking a lot of questions. Have you heard about Steve Smale before? Likely. So he was a legend in topology, got a Fields Medal in 1966, and did a lot in dynamical systems, and he started doing economics. And in the 80s, then he needed to find zeros of polynomials. And he realized that that wasn't just a simple thing. And he wanted to analyze algorithms for finding zeros of polynomials. But the question is, what is an algorithm? So what Smale essentially pointed out as if modern computers really are not Turing machines, and the analysis that people do in scientific computing, for example, if you would like to understand the convergence of Newton's method, is done without a Turing machine, well, maybe we should have a different setup. So what they did, Smale and some collaborator, so this is Smale, this is Lenore Bloom, this is Mike Schub, and here is Philippe Kuker. He is not a co-author on this, he was a co-author on the following book. And this became the BSS machine, the Bloom-Schub-Smale machine. And the Bloom-Schub-Smale machine essentially says, I'm not going to work with integers, I'm going to work with real numbers. And then the computer scientist is going to say, well, that is nonsense because you can't work with real numbers, you cannot work with pi. And of course, these guys are not idiots, and they say, well, I do understand that, but I'm going to split my analysis into two. I'm going to first say, does my algorithm converge? And that means, say, Newton's method. Now, I don't talk about a Okay, back in business. Yes, so their point was that if you wanted to analyze, say, Newton's method, you should pretend that you're working with real numbers. And then at the end, you say, well, now I actually have an approximation. And then you could, for example, use analysis of condition numbers to say, I know that there's a sin that I've committed, but I'm going to do this as a first approximation. So when you talk about the existence of algorithms, you don't talk about necessarily a Turing machine. Okay. I have time for this now because actually I have plenty of time. I just want to mention, do a slight little detour because I want to mention a little bit about Smale's work. In 2014, a guy called Bob Feldman, in collaboration with the Yale University Art Gallery, wanted to do an experiment. So he asked some of the finest minds, in his opinion, I assume, of the 20th century regarding, quote, what was their most beautiful mathematical expression? And the list of people that were asked to contribute here were, super big names like Michael Atiyah, Freeman Dyson, David Mumford. Well, they're all superstars here. Peter Lax, Dick Karp, and also Steve Smale. And the original, so the question was to essentially describe their most beautiful mathematical expression, write it on the board, and that was going to be the artwork. And the originals to this art project is now exhibited at the Institute of Advanced Studies in Princeton. And it's quite interesting if you actually look at what they came up with. And it's given the actual board, or the print, I should say, but also with a description of why they chose these different things. And if you go to the Wikipedia page of Steve Smale, it has a known for part, which is so long that you really have to scroll. It's not a short little page. You have to scroll very, very long because of the all blah, blah, blah Smale things. And it's of interest to see what was essentially Smale's most beautiful mathematical expression. Here it is. Oops. Did you expect that? Okay, so the reason why I want to show this is that in Smale's view, the foundations and the understanding of algorithms for numerics and for foundational computational mathematics is really at the heart of mathematics. This is his opinion. I'm not saying that it's my opinion or your opinion. That's his opinion. And I think it's quite interesting that Newton's method, which actually he certainly did not invent, although he has done a lot of very fine work on Newton's method, is, in his point of view, the best or the most beautiful mathematical expression. So why am I interested in this? Well, when we look at the foundations and the existence of algorithms, if we talk about computer science, then the Turing machine is the mainstay, and that is the foundations. In scientific computing, that is not the case. So you have the Turing model, you have the Bloom-Schub-Smale model, you have integer arithmetic, you have floating point arithmetic. There is not a universal understanding of what is an algorithm in scientific computing. So when I made statements, which was kind of a bold statement, saying that you will have these lower bounds and they're universal regardless of the model, what that means is that you have to come up with a result which essentially says that regardless of what you put on your model, you won't be able to break these barriers. So what I'm going to show you now are parts essentially of a greater program, which is essentially a direct continuation of Smale's program on foundations. And it's about what's called the SCI hierarchy. So Smale did not invent the SCI hierarchy, but this is a direct continuation of all of his questions. And it does not in any way contradict the Turing setup or Hilbert setup. These are just specific examples of this hierarchy. But I just want to give you the motivation for this sort of abstract nonsense. Why do we want to do this? And the reason why you want to do this is that you would like to have something which is completely universal. Right? So this is probably the driest part of what I've been doing in 2 days. So if you fall asleep, I do understand. But please bear with me, because this is hopefully at the heart of understanding how to get the lower bounds. So if we're going to go back and say, we're going to have a framework that allows us to essentially incorporate anything, not only do we have to define what we mean by an algorithm, but we also have to define what we mean by a computational problem. So now we're really getting down to the foundations. So the setup here, and bear in mind that this setup here is for any kind of computational problem that you will ever see ever. That's the idea. Okay? So we're going to start with a set, call it omega. This is called the primary set, and this is the set of input. It can be a set of matrices, say self-adjoint matrices. In our problems that we're talking about in optimizations, it will be the set of A and Y, matrix and the Y, the vector Y, or in linear programming, A, Y, and the vector C, for example. Or it could be something completely abstract. I could have a set of Schrödinger operators here, or some operators on a completely abstract space. So that would be the input that I'm interested in computing with. I can't store a Schrödinger operator on my computer. So the only way I can deal with an abstract object is to have something which can read numbers from that abstract object. So what I need is lambda here, which is the set of complex valued functions on this omega set. And we call that the evaluation sets. If you have the input is a matrix, then you can see the matrix elements, for example. If you have a Schrödinger operator with the potential, well, the way you may read the input could be at pointwise samples of the potential function, for example. So it is very important that the way you read information is a key ingredient in your actual computational problem. And you will have to work with a metric space. So the metric space is there because I need to have a notion of distance. And then finally, there's the fourth component, namely the problem function. This is the function that takes the input and spits out something. So in our case, it takes the input, A, Y, and spits out the solution to the optimization problem. But it doesn't have to be an optimization problem. It could be, I would like to compute, say, the eigenvalues of a matrix, for example, or a solution to a PDE, an ODE, or whatever you like. Okay. And then we can essentially wrap that up and say, these four ingredients define a computational problem. I have my input, I have a way of reading it, there is a mapping here, that psi thing, which I'm actually interested in computing. So I have these 4 ingredients that will define what I mean by a computational problem. And now I'm going to try to solve that problem with an algorithm. And now you go, okay, now this guy has been talking about the Turing machine, a BSS machine. Is he going to create a new machine? And what I want to do here is not to create a new machine. I'm going to take a step back, and I'm going to define what we call a general algorithm, which is much more general than the other ones, so that if you can get a lower bound with this one here, it implies a lower bound for any of the existing theories. Did that make sense? You want to make something which is very general. And the key part here is that this does not require recursion theory. I'm going to get to that in a second. Okay. So I have my computational problem, and then there are 3 axioms for which a general algorithm has to satisfy. The first one is that there only exists a finite subset of evaluation. So I have my algorithm, my mapping here, my gamma, and the input that can read will depend on the input I have A here, so it can be adaptive, but it has to be finite. It's a completely reasonable axiom because I'm going to be working with a digital computer, so I only can access finite amount of information. The second part here is that when my algorithm actually acts on that information, it can only use that finite string. It can't use anything else. It can't call somebody up and say, hey, can you tell me something about the solution to my problem? Right? So these are completely trivial axioms that you'll have to have. But there's a third one. The third axiom is this. Because I can allow this here to be adaptive, that means that I have to do this in a consistent way. So what it just says is that for every b in omega, such that if b of f is equal to a of f for every element here in the valuation set, then the valuation set of these 2 guys have to be the same. And then you're like, what does that actually mean? It means that if you're reading essentially information in, and if you now have read the same thing for another input, well, then you have to have exactly the same kind of input. And if you don't have these axioms, essentially you can do anything. And here's the key part. It is this here that essentially is the driver for all these lower bounds. And this is a weaker condition than a Turing machine. This is weaker than recursion. So that means that if it breaks for this, it breaks for anything that is recursive. So that is the key part. Now, why do I do it like this? Well, we do it like this because we want it to be general. But there's also another plus here, and that is that if you're actually interested in showing impossibility results in scientific computing, they don't happen because of recursion theory or not. They happen because of this. And that means that you actually don't need to read 500 pages of recursion theory to understand these problems in analysis. It actually boils down to this condition here. If you violate that, you can get any kind of results, but the key part is this here. And that means that if you would like to understand lower bounds and essentially the proof techniques used to show impossibility results in optimization or modern scientific computing, you actually only need to work with this, and you don't need to read a lot in logic. And I'm not a logician at all. I do work with logicians, so I ask them a lot of questions, but I'm not a logician. I'm an analyst. And one of the problems that we have, if we're going to talk with logicians and if we're going to make lower bounds, is that we don't have a common language, because I'm educated as an analyst. But you actually don't need that. You only need these axioms here to get the lower bounds. When you have that, you have universal results. Right, I have 15 more minutes, and I think that people are getting a little tired. So I'm just going to wrap up a little bit. So this is just what I just said, that a general algorithm does not apply recursivity, and that means that it's more general which means that actually getting the lower bounds is harder to show, but it's also nicer. And you don't need the logic to work with the SEI hierarchy. I'm going to wrap up. I have a couple of more slides here, and then I think we'll just take questions. Let me just see if I had more. Yes. OK. For optimization problems, you're essentially good. We're just talking about that you may potentially need one limit to solve your problem. There are problems in scientific computing. For example, the problems that I suggested by Smale in one of the earlier slides that was solved by Kurt McMullen. These are problems for which you actually need several limits. And that sounds a little bizarre. But for example, computing spectra of infinite matrices are problems for which you need more than one limit to actually solve. And that's why you cannot have just a general algorithm. You need what's called a tower of algorithm to deal with. And a tower of algorithm is simply a collection of mappings where the only thing that you require is that the lowest one here in the hierarchy is a general algorithm. And then you can march away by passing the limits all the way up to the function you're trying to compute. And there are problems for which you actually need several limits to be able to recover. And it's a barrier that you cannot break. And then you can define what is called the solvability complexity index. And the solvability complexity index is simply the shortest or the smallest height of a tower that you can build. And if you don't have a tower, then the index is infinite. And if you can essentially solve this in finite time, then the index is 0. And I'm going to actually jump a little bit because you are getting tired, and which I totally understand. And what I just want to say is that now you can classify essentially all problems in scientific computing in this hierarchy. So the bottom hierarchy here is delta 0. That is the set of problems for which you can solve in one limit. Without any limit. It is the index has 0. Then there's delta 1. Those are the problems for which you can actually solve, and you know that you have error control. Then there's delta 2, which are the problems for which you may be able to solve with one limit, but you may not have error control. And then delta 3 and so on and so forth are the problems where the index is less than or equal to m. And essentially, this hierarchy here is what you can put anything into. So this is a hierarchy that allows you to describe scientific computing and computer science if you want as well. And this is what we're using to get the lower bounds. And with that, I think I'm going to wrap up and say that there's tons of important lower bounds problems here that if you're interested, I'm more than happy to discuss them with you. But this is a slightly different part of signal processing. But for us to be able to actually have reliable algorithms, we need to understand the lower bounds. And with that, I thank you for your attention and hope there are some questions.
Comments? Yes.
You got me a bit confused about your Kepler conjecture. So,
okay, so let's go back to that.
Just confused about my question, actually. Shouldn't you change your starting point instead of studying your 3 minimization problem? Shouldn't you study the argument of the argmin of your problems and not the mean of your objective function? Isn't your study ill-posed?
So you mean that I'm asking for the argmin that's ill-posed?
Yeah.
Yes, which is the whole point, right? So that is logically non-computable.
Yeah. Getting
the objective function isn't. That is computable.
Yeah.
So the issue was that would that actually have an impact on the computer-assisted proof for Kepler's conjecture? And because there is an issue that the input in these linear programs are not exact. So it's a good question to get that clarified. So The point is that they end up actually computing the objective function. So it is fine. It's good. But there is a reason why they only concluded with 99% certainty. And that is that it wasn't completely clear that they knew, because you needed to get it to 10 to the minus 8. Mm-hmm. So how were they sure that the numerics was done and you can guarantee that you get it to 10 to the minus 8? But our results did not violate that procedure. And I also pointed out, which I want to highlight again, is that even if the problem was formally non-computable, if you wanted 10 to the minus 8 digits, that would still have been fine if you knew that your problem had a breakdown-epsilon that was smaller. So in other words, you could have used a non-computable problem and still checked it if you knew that your breakdown-epsilon was small enough. If that was large, then you wouldn't be able to do it. Did that clarify the...
Yeah, I guess I have a problem of concept, is that you want to guarantee about the minimizer, and yes, we are minimizing the objective function to find a minimizer.
Oh, I understand. But so the issue is that, yes, if I have a minimizer, then I'll immediately have the objective function. If I compute a guy, which is gives me an objective function which is close to the true objective function, that does not imply that I have a right minimizer.
Yeah, sure.
That's the key part. So these are very, very different computational problems.
Other questions or comments?
In the general case, how do you compute the computational complexity? Is the same as in the Turing machine, the running time of the algorithms?
That is a very good point. So now we're getting into the real deep problems here. I have not defined any complexity theory here yet. So this is a very good point. Because, as I mentioned here, I can only talk about a complexity theory when we agree on a halting criterion. So if you are using complexity theory in standard computer science, what you have is a finite amount of input. You run that with a Turing machine, and it spits out something which is exact and true. And you're asking, how difficult was it to get there? That is a well-posed question to ask. But if I'm in scientific computing, and I've essentially suggested that these problems are non-computable, meaning that I don't have a way of halting, I can't talk about complexity theory before I have a halting criterion. And then you can ask, what do I mean by complexity? That I haven't defined. Because we need to get these bounds and talk about computability before we can essentially say, now we're going to sit down and talk about complexity. So, and this is a very deep question. So I'm just suggesting this here as, now if you understand the bounds, then we can talk about the complexity. But in what way should the complexity be defined? Should it be in terms of functional evaluation you use, or iterates, or actual runtime? How do you define your runtime, for example? I have not discussed that at all, so it's a very good point. I'm just saying that at this point now, we can start talking about it. So when we have that, we can talk about what's the fastest algorithm to get to the halting criteria, which is essentially, when do I get my epsilon accuracy? So that might be something that you can contribute to.
Other questions? Okay, so let us thank Anders for the all 4 courses.
Thanks very much.